So you see my screen, right?
Yes, perfect.
So thank you for being here, and of course it's a pleasure to take part in such a beautiful school. So I spent the first two lectures in explaining to you some of the techniques that one can use on the Poisson space in order to control the fluctuations of quantities, and in particular of quantities that have a geometric flavor, by using results that are connected and improve or are an alternative to the Poincaré inequality. There still was a sort of the prism through which I looked at the many results that I have. So as Matthias told, what I want to do today is to describe to you how this variational techniques can be used not only to control variances, but also to control fluctuations in a more probabilistic sense, in the sense of central limit theorems, or more generally probabilistic approximations. And the key is that actually these techniques that are based on integration by parts and then variation inequalities combine quite well with a method, with a theory, sort of theory, probabilistic theory that was developed starting from the end of the 60s, beginning of the 70s by Charles Stein. So Charles Stein is one of the towering figures of mathematical statistics and probability. So the James Stein estimator, Ephron Stein inequality, the James Stein paradox, everything Stein in statistics come basically from Charles Stein. So it was truly an innovative thinker. And at a certain point towards the end of the 60s, while teaching his probability courses in Berkeley, he decided that he was not satisfied with the usual proof of the central limit theorem by Fourier methods. And so he developed his own method, and it turned out that this method was much more far-reaching than the usual central limit theorem, and is actually, it has become a powerful method for deducing probabilistic approximation. That is statements that allow one to compare the distribution of random elements, and the peculiarity of this method is that Stein's method is based on the use of differential operators and differential equations, partial or ordinary differential equations, depending on the situation. And it has a lot of applications ranging from matrix theory to stochastic geometry, mathematical statistics, machine learning. There are really many applications of this method in a number of situations. So here we'll give an introduction to this method, and then in the last part of my talk, I will come back to the formalism of Poisson measures and stochastic geometry. So I will provide an introduction to Stein's method, and I will focus on the simple case of one-dimensional and normal approximation. So something which is close in spirit to the Bayesian theorem that has been already quoted, and which is just a quantitative version of the central limit theorem. And so whenever one presents Stein's method for normal approximation, there is a sort of a narrative that one is like compelled to follow. And this narrative starts with a lemma, which is Stein. Everything is Stein. So there is a Stein lemma that suggests a Stein heuristic, then can be formalized to Stein equations and controlled with Stein's bounds. Okay, so these are 4 steps that are like the canonical steps for presenting the narrative of Stein's method. So in my next slide, I just want to point out that this is a very is a community that spans a number of domains and also a number of generations of probabilists, starting from Louis Chen. He was a PhD student of Charles Stein himself, and then ranging to important names in the probabilistic community, and that I try to order according to some chronological order, which is not at all precise. And also I would like to point out that one important member of this community has been Elizabeth Meckes, and in particular, to which this trimester is dedicated. And also, in particular, there is a version of Stein's method that she developed, which is called the infinitesimal version, infinitesimal approach to Stein's method, that really combines very well, and actually had been applied by people, and it combines very well with the kind of techniques I'm going to describe today, that is in this connection with Malyavan calculus on the Poisson space and Stein's method via the infinitesimal approach by Elizabeth Meckes can really give some very impressive results. And so, unfortunately, we all know that what happened, and we are all very sad about this. So, okay, so the starting point of Stein's method. So let me first focus on the kind of distance I'm going to look at. So I'm going to focus.
Giovanni, I'm sorry. Maybe you forgot to mention Alexander Tikhomirov.
There is a Tikhomirov method, which is a sort of alternative to the Stein's method. I think we can say that. Okay. Yeah, in any case, I'm not gatekeeping Stein's method. I'm for sure forgetting a number of people that gave beautiful contributions.
But Alexander was one of the main, in my opinion.
I apologize about my about this point. I really apologize about this, but I just wanted to point out this intergenerational nature more than focus on precise thing. But thank you very much for telling me this. So I will focus on one-dimensional approximations, and I will choose a distance in order to measure, therefore, the distance between the distribution of random variables, which is a transport distance. It is called the one Wasserstein distance, at least in my lecture. There are other names that are available in the literature. And it is defined as follows. So given two random variables, x and y, both integrable, then I define the one Wasserstein distance between the distribution of x and the distribution of y. So first of all, as the infimum over all pairings of random variables a and b, such that a is distributed as x and y is distributed as x, b is distributed as y, sorry, a is distributed as x and b is distributed as y, of the expectation of the difference in absolute value between a and b. And this one Wasserstein distance has a dual representation in terms of supremum, which is a supremum over all Lipschitz functions with constants less or equal to 1 of the absolute value of the difference of the expectation of h of x minus the expectation of h of y. And actually, this second representation is going to be the one that we're going to apply and use in my presentation. So what I'm going to tell you applies to other distances, like the Kolmogorov distance, the total variation distance in some cases. But this one, for several reasons, is easier to apply without having to specify a number of technicalities. And let me tell you that, of course, this one Wasserstein distance is stronger than the topology in convergence and distribution, in the sense that if you can prove that the sequence of random variables xn is such that the one Wasserstein distance between xn and some other random variable x converges to 0, then automatically the distribution of xn as a random variable converges to the distribution of x. Okay, so it implies convergence in the Wasserstein distance, implies convergence in distribution, but the opposite is not true. So there's a stronger statement. Okay, so I will focus on that. So as I was telling you, there is a certain order in which one can present or usually present Stein's method. So I'm going to denote by Z our target random variable, which is an N01 random variable in general. So center Gaussian random variable in dimension 1, center mean 0 and variance 1. And one starts typically with a lemma. Okay, so it is a very easy lemma that you can prove in a few lines, and it's called Stein's lemma. So Stein's lemma tells you the following. So if you have a real valued random variable Z, then the random variable Z is distributed according to the N01 law, if and only if for every smooth function f, the expectation of f prime of Z is equal to the expectation of Z f of Z. So the proof of this is elementary. So in one direction, so if Z is Gaussian, this identity can be proved by integration by parts. So I'm not specifying the exact degree of regularity of the function f. Is not very important at this point. So this can be proved by integration by parts. And on the other hand, if you want to go in the other direction, so prove that if a random variable verifies this, then it is Gaussian, it means 0 and variance 1. You have at least two rules, actually many rules. You can choose f to be a monomial. And in this case, this relation gives you a recursive relation of the moments of the Gaussian distribution that is determined by the moments. Or on the other hand, you can choose for f a complex exponential. And in this case, this relation gives you an ordinary differential equation, which is satisfied by the characteristic function of Z. And the only solution of this ordinary differential equation is the characteristic function of the Gaussian N01 distribution. Okay, so these are two possible elementary ways to prove this result. So, okay, so this is a characterization of the Gaussian distribution. A few remarks. This, of course, is not the only characterization in terms of derivatives or differential relations of this type of the Gaussian distribution. And on the other hand, if you followed yesterday lecture by John Niemann, so you maybe recall that at a certain point it was mentioned the generator of the Orstein-Uhlenbeck semigroup, and you can obtain the generator of the Orstein-Uhlenbeck semigroup from this relation by just taking adding one order of derivation. So if you take one order derivation, you add one order of derivation here and here, and then you forget about the expectations, and you put a minus here. Then you obtain the generator of the Orstein-Uhlenbeck semigroup in dimension 1. So this operator, I mean this quantities, the difference between f prime and zfz, is tightly related to the Gaussian distribution, in particular via the Orstein-Uhlenbeck semigroup and its generator. Now, after Stein's lemma, there is a Stein heuristic, which is suggested by the lemma. And this heuristic tells you the following. So now suppose that you have a random variable z, such that, so the desired equality between the expectation of f prime of z and the expectation of z f of z is not exactly true, but is close to be true for a large class of smooth functions, little f. So this means that the difference between this quantity and this quantity is small, and actually uniformly small, over a sufficiently large class of smooth mappings f. Then the heuristic, which is the starting point of Stein's method, is that the distribution of z should be close to the Gaussian distribution in some sense. Okay, so there is no a priori reason to deduce the results from the elements that I gave you until now, in particular from Stein's lemma, but this seems like a reasonable conclusion that if a random variable verifies approximately the content of Stein's lemma, then it should be in some sense close to the Gaussian distribution. Okay, so there is a way of formalizing this intuition, which is behind this heuristic, and it is by introducing what one calls Stein's equation. Okay, so the Stein equation are the following. So remember that I'm working with the one Wasserstein distance. So in particular, I'm working with the dual representation and therefore with test functions that are Lipschitz function with constant that is less or equal than 1. So now let's fix one of these H functions, one of the functions that compose the definition, that give you the definition of the one Wasserstein distance, and consider a random variable n, which is distributed according to the n01 distribution. And now the Stein equation, which is associated with the test function h, and of course with the random variable n, is the following. So on the left-hand side, you have f prime of x minus xf of x, which is equal right-hand side to h of x, expectation of h of n. So the unknown function is f, and actually what we are looking for is a function of class C1 that verifies this relation for every x in R. Okay, so a solution is given by that. And the function h is known. So it's one of the test functions of the composing the one Wasserstein distance, which is fixed. Now this differential relation is equivalent to a relation which is which is very easy to manipulate, and it can be obtained in the following way. So I can take the right-hand side and the left-hand side of the Stein equation, and I can multiply by side by the exponential of minus x squared divided by 2, exponential of minus x squared divided by 2. And in this case, the Stein equation is equivalent to the second line in my slide, which is equivalent to the relation, the derivative of exponential of minus x squared over 2 f of x is equal to the exponential of minus x squared over 2 h of x minus the expectation of h of n. And now I can simply solve this equation by integrating both sides. And by integrating both sides, I obtain that every solution f of the Stein equation has necessarily the form c, some real constant, exponential of x squared over 2, plus the exponential of x squared over 2, the integral from minus infinity to x, and then h of y, minus the expectation of h of n, and then exponential of minus y squared over 2 integrated in dy. Okay. Now, so all these solutions are legitimate solutions, but there is one that is typically chosen as the canonical solution of the Stein equation, which is obtained by taking C equal to 0 here. So by deleting this term. And the reason is that, so we are going to work and to use this function in particular. And the reason is that all the other solutions are such that if you multiply them by the exponential of minus x squared over 2, and you take the limit for x going to infinity, then the product of every other solution is convergent to x, to c, to the constant c, to the constant c, except, and of course, if one takes c equal to 0, then one has a convergence to 0, which makes several computations easier, and also makes things easier in order to deal with integrals and expectations. So the canonical solution of the Stein equation associated with the test function h is this function, fh of x, which is therefore the exponential of x squared over 2, the integral from minus infinity to x, and then hy minus the expectation of hn, and then exponential of minus y squared over 2 integrated in d. Now, the key point of this, so all this is just an equation that we solved, and it has a nice form. We started with an easy equation, we ended up with a solution that has a nice and explicit form. And now the key point of Stein's method, the key estimate of the key result that brings the lemma, the heuristic, and the ordinary differential equation that I wrote here together, is that one can control uniformly the regularity of these functions here. And this is actually quite an easy exercise that I'm not doing in front of you, but you can check on any reference or even by yourself, because it's really quite an easy computation. That is, one can control uniformly the regularity of these solutions fh of x over the whole class of Lipschitz one functions that enter the definition of the one Wasserstein distance. Okay, so more precisely, one can prove the following. So this is not proved, but the proof is quite easy. Is that by direct inspection of that, one can show that therefore the function fh that I just defined is a C1 function, so it's of class C1, such that the absolute value of the first derivative is bounded by 1 for every function h. So this is something that I should write here. So for every h of class lip 1, so this and f prime is a Lipschitz function with Lipschitz constant that is less or equal to 2. Once again, for every h in the class Lipschitz 1. So these are two estimates that can be done by just looking and working a bit with the explicit expression of this canonical solution. In particular, it is useful in general to use the fact that if you let x that this integral for x going to, so this integral from minus infinity to infinity is equal to 0. Okay, so you can actually replace this integral by minus the integral from plus infinity to x, for instance, and work with that. But in general, this is the key point. Okay, so for every function h in the Lipschitz in the class Lip 1, so the first derivative of the canonical solution is bounded by 1, and the Lipschitz constant of this first derivative is less or equal than 2. So this is a phenomenon that is really not just applying to the one Wasserstein distance. So there are other and even probably more attractive distances in probability theory, like the Kolmogorov distance, or the total variation distance, for instance, in dimension 1, or a higher dimension. There are other distances, like a complex distance. And for all these distances, there is, in general, the possibility of proving uniform bounds on the solution of the Stein equation. Okay, so uniform bounds that therefore allow one to do some specific computations that are leading us to effective probabilistic approximation. So now we prove that, and we prove all this chain of of relations. And now what can we do with all these relations? So we can deduce the following estimate. So remember that we want to compare in the one Wasserstein distance the distribution of some random variable integral x and the Gaussian random variable n. Now let me also assume that the expectation of x is equal to 0, and you will see later that this is not this is something that has to be done. And now the one I'm using here the dual representation of the one Wasserstein distance, which is given therefore by the supremum of all h in the class LIP1 of the absolute value of the expectation of h of x minus the expectation of h of n. Right. Now the guy here is exactly the right-hand side of Stein's equation. Now, since I solved for every x since I solved Stein's equation associated with h, I can replace the right-hand side of the equation with the left-hand side of the equation, right? So this means that inside the expectation here, I can put instead of h of x minus the expectation of h of n, f prime h of x minus x f h of x. So I replace simply the right-hand side, I swapped the right-hand side with the left-hand side of the Stein equation. And now, final point, I can put forward the regularity that I just stated of each canonical solution of the Stein equation, in particular that f prime infinity is less than 1 and f second infinity is less than 2, to say that, okay, this supremum here can be bounded by the supremum over all functions such that f prime is bounded by 1 and f second is bounded by 2 of the absolute value of the expectation of f prime of x minus x f of x. Okay, so, and this is Stein's bound. So this is what the Stein bound in dimension 1 associated with the one Wasserstein distance. So why is this remarkable, and why are we in a better position than we were before knowing Stein's method? So the first point is that, the first point is why this is remarkable already. And it is remarkable because we started with an expression that involved two random variables, x and the target random variable n. And at the end of the day, we ended up with an expression that only involves one random variable, the random variable x. That is capital N, the target random variable, that disappeared. So the role of the target random variable n now has been replaced by this operator, f prime minus x of x, that characterizes the Gaussian distribution. So there is no n anymore, but there is the quantity that characterizes the distribution of n. And now, so this is some sort of theoretical interest. Then let me make a remark. The remark is that if x is not centered, okay, and since I'm taking a supremum over derivatives, over functions such that the derivatives verify some bound, I can replace f with f plus c for every constant, and therefore this bound becomes infinite if x is not centered, because I can replace f with c plus f for every real c, and therefore, I mean, a necessary condition for this bound to be meaningful is that the expectation of x is equal to 0. Okay, so this is a remark. But now the key point that makes this bound useful for application is that the typical way of working this bound is actually to go in this direction. That is to find a way to rewrite this expectation of x f of x in a way which is as close as possible with the expectation of f to the expectation of f prime of x. Okay, so we are in this situation here. We write this as a difference of two expectations, and we want to transform the expectation involving f into something that is close to the expectation that involves f prime. And now, since we work with the second expectation, that is with the expectation that involves f, we can actually use an additional degree of regularity. That is, here we started with a collection of test functions that were of class Lipschitz 1, and here we are ending up working with test functions or expressions that involve functions f that has one additional degree of regularity. Now, this is a C1 function with a Lipschitz second derivative. And this is really useful, and we will see immediately that this is useful for explicit applications. Okay. So, as I was anticipating, there are many techniques that have been applied according to the situation in order to go from this point to this point. So to move from this expectation to this expectation. So many techniques are techniques that involve pairings, that is the construction on a possibly enlarged probability space of another random variable, let's say x prime or x star, that either is distributed as x and such that the vector x star is exchangeable. So this is known as the technique of exchangeable pairs, or random variables that verify some identity as far as expectations are concerned. So these are called the size bias transforms, zero bias transforms, or often also these kind of expressions are controlled by using the notion of dependency graph. This is something that I'm not really going into. So the kind of approach I'm going to describe is a more analytical approach in the following sense. So whenever you have to build a pairing of your random variable that you want to control the fluctuations of, and another random variable, you have to have a full understanding of the probabilistic structure of your model. So you have to have really a very advanced information about your model. And what we are doing here, we are just applying the techniques, the integration by parts formula that come from these techniques related to Malevin calculus. And this does not require that we build any additional noise, any additional randomness in our model. So let me also quote that there are several applications of Stein's method to the concentration of measure phenomenon. And this started in 2007 with a paper by Chatterjee, and several other authors like Larry Goldstein also worked on that. And let me also tell you that everything that I told you in dimension 1 extends to probabilistic approximation in several dimensions, for vectors of random variables. And so there is an associated Stein's partial differential equation, and we have more and more techniques that allow us to deal with challenging distances, like for instance, the convex distance, etc. But there is still something which is challenging, which is how to develop an infinite dimension, so a version of Stein's method that applies to infinite dimensional situations, like functional convergence, for instance, in the case of continuous function of Cadillac functions, etc. So there are several papers that work in this direction. Several were developed in the last maybe 5-6 years, but we are still far from having such a nice and like to say smooth picture as we have in the finite dimensional situation. Okay, now how this combines with everything that I said yesterday. So let us remember the framework. So we start with the Polish space. We consider a locally finite measure on our Polish space, and then a Poisson measure that has lambda as an intensity measure. So I told you that, and I described to you the role of the add-one cost operator, which consists in taking a random variable f depending on the Poisson configuration by adding 1 point to the Poisson configuration and subtracting the original value of the variable. And then in my previous lectures, I commented and used a bit the generator of the Ornstein-Uhlenbeck semigroup on the Poisson space. I introduced the pseudo-inverse. I described at least spectrally the pseudo-inverse. And then one of the results that I told you are fundamental for the whole theory to develop is this integration by parts formula that tells you that if you take the expectation of L of G for G in some good domain, multiplied by F for F sufficiently regular, then the expectation of L of G times F as a consequence of Mecke formula is equal to minus the inner product of the two add-one cost operators in the L2 lambda space. Okay, so it is minus the integral of d plus g and d plus f integrated with respect to lambda. Okay, so this was the what I call the integration by parts formula on the Poisson space, and this is the moment where we are going to use this integration by parts formula. Now, I want to tell you how this integration by parts formula can be used in order to accomplish the task of going from this direction, from this point to this point, in some reasonable way in the frame of Stein's method. And it goes as follows. So now, consider a function f from R to R that has the degree of regularity, which is the same as the one of the canonical solution of the Stein equation for a Lipschitz one function. And consider a function of, which is a square integrable functional of the underlying Poisson measure. Assume that this function has mean 0, and also that this condition, which is necessary for having integration by parts, is verified. And now our goal will be to compare f with a Gaussian, with a distribution of a Gaussian random variable with mean 0 and variance 1. Now, we start with this. We have the expectation of f, little f of capital F. And now what I can do, since f is centered, I can write f as L, generator of a Hausdorff semigroup, composed with L minus 1 times. So this is true only if f is centered. And then I keep this as it is, f of capital F. Now I can apply directly integration by parts. So I have L of L minus 1f multiplied by f of capital F. And can I apply integration by parts in this framework? So integration by parts is also written here on the lower part of my slide. And this, as I was telling you, is equal to minus the integral d plus little f of capital F times d plus of L minus 1 of f integrated with respect to lambda. Now, this d plus, what is d plus? So we have d plus of f of capital F in x. So this is simply f of eta plus delta x minus f of eta. This is how the add one cost operator is defined. And I can therefore apply a Taylor expansion at the order 1 because I have the correct degree of regularity. And so I can write this as f prime of f multiplied by d plus f and then minus d plus L minus 1 of f. So I brought the minus inside the inner product. And then I have a residual term, a remainder. And this remainder is controlled by the Taylor expansion and by this bound on the second derivative by the 2 simplifies with the 1/2 in Taylor. And this gives me the expectation of d plus f square. So this comes from the Taylor expansion. And then the term that is already here, which is the absolute value d plus L minus 1 of f. Okay, so I really used completely the nature, the smooth nature of the solution of the Stein equation. Now, since I have written this expectation as something that involves f prime times a remainder, then I am in a situation which is closer to what I wanted, and I can actually go do and accomplish the task I was telling you before, which consists in the following computation. So I have the one Wasserstein distance between f and n. I bound this as I did before with the supremum over all functions such that f prime is bounded by 1 and f second is bounded by 2. Absolute value of the expectation of f of capital F minus f prime of f. And then I can just apply the previous computations, that one coming from the other page. I can bound f prime by 1. And therefore, what I have at the end of the day is that this one Wasserstein distance is bounded by the expectation of the absolute value of 1 minus the inner product of d plus f minus d plus L minus 1 of f. And then plus the expectation of d plus f square, absolute value of d L minus 1 of f. Everything is integrated in d lambda. Okay. So we proved this result in 2010 with Soleta for MZ. And also observe that still by integration by parts, the expectation of this guy here, so I can go backwards in my integration by parts formula, and the expectation of this guy here can be proved immediately to be equal to the variance of f. Okay. So in particular, if the variance of f is 1, then this is actually the first absolute central moment of this inner product. Okay, now this is the point where, so in particular, since this is an expectation in L1 norm, I can bound it with an L2 norm. And I have also to close WhatsApp because it's just doing beep all the time. And so I can actually control this term. So whenever 1 is equal to the expectation of this guy, by Cauchy-Schwarz, one can control this term by means of the Poincaré inequality I was describing so eloquently in the previous 2 lectures. Okay, so therefore to describe what I'm telling you, I'm going to do the following. So I take this guy here, I bound it with the by the Cauchy-Schwarz inequality, by the L2 norm, by its L2 norm, and then by the triangle inequality, I can just bound this guy by 1 minus the variance of f, and then by Poincaré inequality, by the expectation of d plus applied to this inner product here, squared, because this is the Poincaré inequality, integrated with respect to lambda. Okay, so this term here is controlled by the triangle by Cauchy-Schwarz, Poincaré inequality, and the triangle inequality. Okay, and so we are in a situation, therefore, where we have d plus of the inner product, and this inner product involves d plus of f times d plus of L minus 1. Now, this L minus 1 of, so this, everything here has a nice form in the sense that all these d plus operators have a very clear geometric meaning. So we can actually develop in principle geometric application. But there is one hair in the soup, is that this L minus 1 is in principle not very explicit. So there is a way, so we know that this L minus 1 of f has a spectral representation. Also, it can be represented in terms of the Ornstein-Uhlenbeck semigroup, and therefore one can take advantage of the Meller formula. But in principle, it's quite it's a task to deal with this, except in the case where here we have explicit access to the chaos decomposition of a given random variable. So we know explicitly how these projections behave. Then this term becomes amenable to analysis. And in particular, several applications by many authors, Matthias Reisner, Matthias Schulte, Lachièze-Rey, Christoph Taylor, Daniel Hug, Günther Last, have used this fact, the fact that for many geometric quantities, and thank you to the last Penrose formula I was quoting in the first part of my lectures, this object here is amenable to analysis because one has explicit access to the chaotic projection. But this is not always the case. So in many occasions, this is not doable, and therefore one has to develop some other tool in order to deal with this L minus 1, and in particular with the fact that we are dealing with this second order, with sort of iteration of the add-one cost operator. Now, how to do this? And so this will be the last part of my talk. And so how to deal with this object here? So what kind of estimates one would like to have in a Poisson situation as an application to geometric quantities, whenever this L minus 1 is not directly amenable to analysis. And so one can actually do this, and one can actually develop quite a nice collection of results by taking inspiration from what happens on the Gaussian space. And so, I would like therefore to discuss this theme, which is the notion of a second order Poincaré inequality, by first describing quickly to you what happens on the Gaussian space, and then by telling you what happens on the Poisson space. So the Gaussian situation is related to a paper from 2009, once again by student Chatterjee, and the situation in the Gaussian space is the following. So consider a d-dimensional Gaussian vector of IID N01 random variables, simple situation, but the relation, this can be really relaxed. And consider now a mapping from RD to R, which is sufficiently smooth, and then define capital F to be psi of G. So this mapping psi, non-linear mapping, in general is a really non-linear mapping applied to the function and to the vector G, and assume that the expectation of this random variable is equal to 0. Now, when you work on the Gaussian space, you can actually define exactly the same formalism, replacing, an analogous formalism, replacing the D plus for the add one cost operator by the natural gradient, verifying a natural chain rule. And in this case, the task of transforming this quantity in a quantity which is suitable to analysis, for analysis via the Stein's method, in the framework of Stein's method this task is easier actually, because you have no remainder term, because you have an exact chain rule. So in the Gaussian space, if you take F sufficiently smooth, the expectation of capital F, little f of capital F, for F defined here, can be actually written exactly as F prime of F times the gradient psi of G, and then minus nabla L minus 1 psi of G, where L minus 1 is a pseudo-inverse of the generator of the Orstein-Uhlenbeck semigroup that already appeared yesterday in Joe Neiman's paper. You can prove this in a very similar way to what I did on a Poisson space, and therefore the task of assessing the distance to Gaussian of a random variable f of this type is actually easier on a Gaussian space. Now, in particular, if you take for little f here, the identity function, so f of x equal to x, then of course f prime is going to disappear. You are here, and then by using the properties of the Orstein-Uhlenbeck semigroup, in particular the contractive properties of the Orstein-Uhlenbeck semigroup, one can obtain the usual Poincaré inequality on the Gaussian space. That tells you that the variance of psi of G is less or equal than the expectation of nabla pi of G Euclidean norm to the power 2. So this is the usual Poincaré inequality on the Gaussian space. Now, in order to understand what I want to do in the framework of Stein's method, one should give an ad hoc sort of interpretation of the Poincaré inequality. That is the following. So what does Poincaré inequality tell you? It tells you that if you have a mapping of a Gaussian vector psi of G, such that the gradient is very small, then psi of G is close to a constant mapping, and therefore the variance of psi of G should be close to 0, right? And the Poincaré inequality gives you a quantitative way of assessing this kind of remark. Now, the intuition which is behind, at least in the Gaussian setting, behind the second order Poincaré inequality, is that now if you have a mapping psi, such that the Hessian matrix of psi is negligible in some norm with respect to the gradient of psi, then psi is going to be close to an affine transformation, and therefore psi of G should be close to a Gaussian random variable, because affine transformations of Gaussian vectors are Gaussian random variables. Okay, so more precisely, in a paper of 2007, Chatterjee proved that in the previous framework, if the variance of f is equal to 1, and if n is our target random variable of order with mean 0 and variance 1, then the one Wasserstein distance between the distribution of f and the distribution of n can be bounded as before by the square root of the variance of this guy, and then by careful use of arguments of the Poincaré inequality, and then Cauchy-Schwarz, one can prove that this variance here, and therefore the one Wasserstein distance, is less or equal than twice the expectation of the operator norm of a Hessian matrix of psi computed in G to the power 4, power 1/4, and then the expectation of the gradient of the norm of the gradient of psi of G to the power 4, and then expectation to the power 1/4. Now, this L4 norm is bounds from above the square root of the right-hand side of the Poincaré inequality, and therefore is bounded from below by the square root of the variance of psi of G. And we are assuming that this variance is close to 1. Okay, so this means that this term here, this factor in inequality, is commensurate to the variance of psi of G, where it take to be not negligible. And therefore, the only way in which the right-hand side of this inequality can be small is that this L4 norm of the operator norm of the Hessian matrix is close to 0. And so if this Hessian matrix, this operator norm in L4 of the operator norm is close to 0, then the Wasserstein distance of f is close to n. And the intuition behind this is that if this factor here is small, then psi is close to an affine transformation, and therefore it has to be close to Gaussian, right? So so this is what happens on the Gaussian space. And so the question now is that we would like to develop, or one would like in principle to develop a similar results on a Poisson space, but with the additional challenge that affine transformator linear functionals of the Poisson measure are not close to Gaussian in principle. So there is a part of my syllogism, my reasoning, which is not going to be conclusive on the Poisson space. And so, but we actually managed to work with this, and in a paper that we wrote in 2016 with Günther Last and Matthias Schulte, so we actually managed to control this by means of the Poincaré inequality, and to write a version of this bound that is an actual second order Poincaré inequality on the Poisson space. So, and the result is stated here. So if you take a function f, which has mean 0 and variance 1, satisfies some additional requirement in terms of regularity, then the one Wasserstein distance between f and n is bounded by all these three terms. So these are a bit difficult to read, not because they are particularly complicated, but because there is a lot of there are a lot of symbols, but every one of the terms here responds to one of the requirements I was heuristically putting forward before stating the result. So in particular, this term here is small if the iteration of the second add one cost operator, so the second iteration of the add one cost operator to f, is small or negligible with respect to the first add one cost operator. Meaning that in this case, our function f is close to a linear functional of the Poisson measure. So this second term here controls the absolute magnitude in some sense of the second order add one cost operator. And now this third term that appears in our bounds is actually a term that can be interpreted as more or less a term similar to what we call, that is close to 0 whenever something close to the Lindbergh condition in the Lindbergh central limit theorem is verified. So remember that if you have a sum of independent random variables, then basically the Lindbergh theorem tells you that you have that they verify a central limit theorem if none of them is, so if the contribution to the sum of all of them converges uniformly to 0. And this is some version of the Lindbergh condition as applied to Poisson measures. Okay. So this is a second order Poincaré inequality on the Poisson space. So once again, the expression is a bit complicated to read, but the important point is that by doing so, we have eliminated the L-1. So the L-1 operator that was there before has disappeared from the picture, and actually all the expressions here has a clear and a geometrical meaning, geometrical interpretation that makes them amenable to analysis. So do I have some more minutes or it's finished? Probably I started a bit later than exactly.
2 more minutes?
Yeah, 2 more minutes. Yeah, good. Okay, so it's a second order Poincaré inequality. So, okay, so the proof is based on Miller formula on a certain representation of L-1. So I would like to point out that there are several extensions at least in 2 directions. So there is a paper by Lachièze-Rey and Yukich that makes a precise connection with the theory, geometric theory of stabilization. So it's a very powerful collection of results with a number of applications. And also there is a paper that really I like very much by Matthias Schultz and Joe Yukich, where they actually provide a multidimensional version of that. So for multidimensional central limit theorem, and they do it in the quite hard to use convex distance. This is the supremum over all convex sets, where the test function are indicator of the convex set of RD. And in order to do that, they develop a genuine new idea, sort of a bootstrapping method for controlling the solution associated with these indicators functions. And in general, let me tell you that this method here is organized in such a way that it gives reasonable bound that we can believe to be optimal in the convergence in several distances. And in particular, it applies to the Kolmogorov distance. So not only to the Wasserstein distance, but to the Kolmogorov distance. And so just an overview of applications very quickly. So there are applications to the nearest neighbor graph in our original paper, where we were able to improve a number of existing bounds in the speed of convergence. There is an equally admirable paper by Matthias Schultz, Christoph Thele about radial spanning trees and edge functions of radial spanning trees. And several other applications are contained in this page, that I will put forward. And that I will put online, we will put online. And let me just finish by quoting the fact that all the ideas behind this Mallev integration by parts approach to Stein's method were generalized at a certain point, starting from the paper by Michel Ledoux, and then by another paper by Asmodee Campese-Poli to the framework of Markov triples, so the really Markov semigroups. And in particular, in a paper joint with Michel Ledoux and Ivan Nurdan, we were able to develop several improvements of function inequalities like Talagram inequality and Otto-Vidan inequality. And there is also contribution to transport inequalities in the recent work with Goslan and Reed. So it really goes in several directions. This approach goes in several directions. And thank you very much. I'm sorry for taking a couple of minutes.